Hello, I'm James Bonnie, the 2020 chassis lead for Ampeter Electric Racing. And first, I'd like to give a shout out to all of my sub-team members for their hard work over this last quarter. Last quarter, we completed the design of the Ampeter 2 chassis in compliance with FSAE requirements with all-around improvements to vehicle performance and driver safety. As you can see, our assembly is made up of 84 complex members, each with its own unique profiles and angles within three-dimensional space. This makes manufacturing a difficult process, but our team was more than able to meet these challenges over the last quarter. Refining a manufacturing technique prototypes in the previous year, we developed the Ampeter manufacturing jigs to fully build this year's chassis using DFM and DFA principles to ensure the highest degree of accuracy. The system uses laser-cut MDF sheets to create freestanding structures that require zero fasteners to function properly. This allows our team to assemble the entire vehicle in 4 different sub-assemblies, enabling us to create a chassis using several independent manufacturing integration groups with an emphasis on social distancing due to the ongoing pandemic. The additional time and energy needed to design these fixtures allows us an unparalleled degree of accuracy during fabrication and the ability to plan out assembly procedures down to individual tubes before the first chassis member has stepped foot in the lab.
Hello, my name is Salman. I'm the manufacturing lead for chassis. In last year's manufacturing process, each engineer will profile one tube at a time, which is really time consuming. This is challenging for us this year since we only get 2 hours per shift due to our COVID safety measures. We made a new 5-stage manufacturing process to emphasize efficiency and mass production. Before our lab hours, we made a list of tubes and their tube templates using SolidWorks drawing. Stage 1 is tube cutting. One engineer will focus on cutting while the other focus on measuring, marking, and tagging each tube with their unique code. The second stage is labeling profile templates. A standard line would be drawn across each tube, and this line would limit the phase tolerance to be under half a degree. In stage 3, the engineer will cut along the profile line using a cutting wheel. In stage 4, a finer profile will be made using a grinding wheel. And this is where we are currently at with about 90% of our tubes. In stage 5, profiles will be further refined using hand tools until they lay flush against each other in the manufacturing jig and ready to be welded. This is it for chassis. We will move on to suspension.
Hello, my name is King Choi, and I'm the suspension lead for Ampeter 2. To begin, I'd like to thank my team for their hard work and dedication during the tough times. From the left, Lucas, myself, Fiona, Braden, and Dean. We began our design in the spring, which we finished in the summer, and are currently in the process of manufacturing for the fall. During the summer, we finished our initial model for the suspension geometry for Ampeter 2, which led to modifying our CAD model of the master suspension assembly. The figures to the right show an angle of the geometry in 3D and 2D with the master suspension assembly in Figure 1. We will also be reusing the majority of the upright assembly with the newly designed steering fixture shown in Figure 5. Accounting for the wider track width, the rocker arm ratios have been adjusted through hand calculations shown in Figure 4. We began the fall picking up where COVID left us off at, which was the assembly of Ampeter 1. Shown in Figure 1, we fit the snap rings into the ball cups after disassembling the wheels and tires, plus the uprights, and our hardworking members are shown in Figure 5. From then on, most of our assembly were to add specific components such as the wheel spacers, camber spacers, then reassembling the components onto the vehicle. We created a test plan to acquire important data from Ampeter 1, which we have categorized into static testing, dynamic testing, and track date testing, all within the standards of FSA rules and regulations. Once we acquired the raw materials for the control arms, we cut and profiled the steel tubes according to the dimensions we have designed on SolidWorks. Attached are the tube parameters, meeting our standards for dynamic scenarios. The template used is a 1-to-1 ratio printout shown in Figure 1, which is taped onto the wooden jig shown in Figure 2. We cut and profiled the tubes shown in Figure 3. Once all the tubes are cut and profiled for all 4 quadrants of the vehicle, we have placed them into the jig and are prepped for welding in the winter, shown in Figure 4. During the fall, there were unfortunate stops along the way due to COVID, restricting access to the engine lab and ultimately reducing the time needed to work on these race cars. Because we may have limited access to the chassis, we have created a solution to limit human contact while allowing members to integrate the suspension onto the chassis. This method will be structured through the use of what we have designed called an independent suspension subassembly jig, which is shown in Figure 3 and 4. These jigs have been designed and are ready for manufacturing for the winter using wood as the structural material. While the jig is fortifying the suspension assembly at right height, we will weld the mounting tabs onto the chassis using the mounting scheme design shown in Figure 1 and Figure 2. Our plan for the winter is to continue manufacturing after testing and acquiring data off of Ampeter 1, disassembling all reusable components with the finished control arms with complete welds and press-fit bearings for Ampeter 2, fabrication of an independent subassembly jig, including cutting and profiling steel square tubing for mounting tabs, followed by a complete system integration, and ultimately staying safe and healthy. Thank you for your time and consideration.